Today we have a very special guest with us, Dr. Robert Brown from Iowa State University. Dr. Brown is an expert in the field of biofuels. In particular, his expertise has been on thermochemical conversion of biomass to biofuels, and that's what he's going to talk about today. One of our sponsors I'd like to mention today is a grant from the USDA that's titled Send USA. And that's a USDA grant that is a multi-state grant run from Iowa State University, working on both production and conversion of biomass to biofuel. So with that, I will introduce Dr. Robert Brown to get us started. Thanks for joining us, Robert.
Thank you, and I'm happy to be here presenting this Send USA webinar. I'd like to talk about a topic that a lot of people aren't very familiar with, and that's what we call the thermochemical option, or thermochemical production of biofuels. This is the notion of using, instead of enzymes and fermentation organisms, using heat and catalyst to affect changes in biomass that allow its conversion into biofuels. So I'm going to start by simply asking, what is the perfect energy carrier for transportation fuel? So we're all used to the notion of gasoline. We can easily pump it into the automobile fuel tank. But if we step back and ask, what are the properties that make us want to use some form of energy for the purpose of transportation, we include these properties listed here. We want it to be a liquid. It turns out that's a perfect form rather than being a solid or a gas. And we don't want it to mix with water. That's one of the issues that ethanol has today, why some people criticize ethanol. We don't want it to be toxic. That's why we don't use methanol. We want high energy density. That's a problem with hydrogen, for example, as a fuel. It's low density. Want it to be able to operate in cold weather. That's my introduction to what the perfect fuel is, and we have what we call a drop-in fuels, which are fully compatible with existing fuel infrastructure. This does not include ethanol because it is not perfectly compatible with the gasolines that we use. So a drop-in fuel should be a hydrocarbon, or it possibly could be a higher alcohol like butanol. Or do these fit the definition of a perfect fuel? And my answer was it's close enough. So we want to produce a fuel, but we need to know what we're going to produce the fuel from. There are three kinds of biomasses. These can be utilized either from a biological process like fermentation or the thermochemical. So I think it's important, though, to recognize what our choices are, and these include lipid-rich biomass, which I'll describe a little bit more, lignocellulosic biomass, and waste biomass. And waste biomass is just a combination of lipid-rich and lignocellulosic and paper and leaves from your yard. It's all kinds of possibilities. I'm not going to talk about that too much. The lignocellulosic feedstock is illustrated here, and this is, if it was turned over to an engineer, they'd say, well, this is an engineered composite, because it consists of fibers of cellulose, and those are the kind of the purple lines shown there in the drawing, that are laid out in a fashion that if they're embedded in a matrix, then it will be a very strong, flexible material, and that matrix that is something called lignin. And that's a natural polymer in biomass. But this material is very difficult to break down because nature intended for it not to be broken down. It's intended to resist biological attack. And so using biology to break down lignocellulosic biomass is a very daunting task. And that's one reason I advocate thermochemical, is because that's one thing nature has devised, is a fire to break down lignocellulosic biomass. Lipid feedstocks are really a neat feedstock in that they are almost hydrocarbons. And this chemical formula shown here is the structure of something called triglyceride. which is found in soybeans and microalgae. And if you start counting up, you'll see a lot of carbon and you'll see a lot of hydrogens, and you'll see only a very rare oxygen molecule, O, on the right side of the figure. And so it doesn't take too much effort to pull those O's out, and once you have the oxygen out, then you have a pure hydrocarbon. So that's the beauty of these feedstocks, lipid feedstocks. Now this question is, so should we be using lipids or should we be using lignocellulose? And from what I've described, it would seem like we ought to be focusing on the lipid feedstocks. But this is to illustrate that if we want to produce lipids versus, or produce hydrocarbons, if we start with carbohydrate, which is shown, the chemical formula shown up in the upper left-hand corner, we're going to have to put it through plant number 1, which is something the engineers build. And what they do is end up extracting oxygen off of this, off the carbohydrates in the biomass. And at the plant at the bottom is shown a pure hydrocarbon. You notice there's no oxygen there. So engineers know how to do that, but plants also are able to do that. And this is the thing to remember, that if you want to produce a almost hydrocarbon in a plant, it actually has a biosynthesis pathway that's illustrated there in blue and pink that involves taking carbohydrate, glucose shown at the top, and going through a cycle that, like plant number 1 shown on the left, spits out oxygen, in this case in the form of carbon dioxide. It's what we call deoxygenating that glucose, that carbohydrate, and ending up with, you'll see in the figure there, a lipid. So we either can start with lignocellulose and build a plant to do it, or we can grow plants that are able to produce the lipids. But there is energy involved in both of those processes, and I frankly don't know which one of these is the better process to look at. So that's a decision that will ultimately have to be made. Now, if you look at the whole renewable fuels industry and all of the different approaches, there are many ways. So on the left are all kinds of feedstocks that we could look at, and in the center are the technologies that could be applied to break them down. At the bottom, you'll see biochemical conversion, which is the idea of using biology to do it. And then there's different kinds of biofuels. And I'm going to focus on hydrocarbon fuels because that fits the definition of drop-in fuels, one that would allow us to greatly expand the biofuels market, because we can only put so much alcohol into our vehicles. It's on the order of 10 or 15%. We have to have a lot of changes in engines to get up to 85%. It'd be a lot easier for the consumer if they didn't have to worry about what their fuel was, what their engine could do, that they can simply use these so-called drop-in fuels. So let's talk about thermochemical biofuels. I like to refer to this as the other cellulosic biofuels because most of the emphasis has been trying to convert the carbohydrates in lignocellulose into sugars that can then be fermented. We're going to look at 2 different kinds of substrates other than sugars, and one of them is syngas, and we get that through a process called gasification. And on the right there at the top photograph is of a gasifier at the Biochemistry Research Farm at ISU. And the other approach is to produce something called bio-oil. This is a liquid that's produced by a process called fast pyrolysis, and that's illustrated at the bottom right of the figure. So if we look at this as a general idea, is we start with a feedstock on the upper left and end up with a biofuel on the lower right. And we've got to have processes that get us there. The first thing we would look at is depolymerizing or decomposing the feedstock into molecules that are appropriate for some final conversion biofuels. So the center circle is labeled thermolytic substrate. That is, we have something comparable to sugars that then we send to a fermenter. But in this case, we'll look at different kinds of processes, and we'll call those processes upgrading to get the desired fuel. So I've mentioned gasification and fast pyrolysis. That's going to be the emphasis of my talk. There are other technologies that in some respects are subsets of these or generalizations of these, but I'm going to just focus on gasification and fast pyrolysis. So this slide shows the process of gasification, which is the thermal decomposition of any kind of organic matter into flammable gases. It is something akin to combustion, but instead of just producing flue gas, carbon dioxide, and water, it produces flammable gases, things like hydrogen, methane, carbon monoxide instead. And the process is interesting in that it can consume virtually any organic feedstock that you throw at it. It doesn't care if it's leaves raked from your yard or switchgrass grown or wood or just about any type of organic material. And here's illustrated two of the major gasification options. There are other kinds of gasifiers, but they tend to be for very small applications. The nice thing about these two reactors is they scale. They scale to plants that could easily be sized at 2,000 tons per day, for example. On the left is what's called a fluidized bed. It takes biomass and injects it into a bed of sand that has air injected in the bottom, so it behaves like a fluid, hence the name fluidized bed. Very good mixing, very good heat transfer, and the gases are released and go out through the top of this reactor. This has actually been the reactor that has been used the most with biomass. On the right is what's called an entrained flow gasifier. It's really a very simple idea. Let's just blow biomass in with oxygen into a hot environment, and as it sweeps along, it turns into a gas, and we can control the temperature with various ways of controlling the oxygen or steam that's put into the system. Seems like a simple system. It is actually fairly difficult to engineer, and it really works best in a very, very large-scale systems. It has not been proven out very well with biomass. It works very well with coal because it turns out biomass is actually easier to gasify than coal. But there is work trying to adapt this to biomass. The product of gasification is syngas, short for synthesis gas. As I've already stated, it's mostly carbon monoxide. Hydrogen carbon dioxide is a product, as is methane. Well, that's wonderful because we can use that then to synthesize useful compounds from it. The difficulty is syngas contains a lot of contaminants, and I've listed here tar, alkali metals, sulfur, nitrogen, and chlorine. And it'd be nice if we had one process that removed all of them, but I'm trying to illustrate here at the bottom, it actually takes a separate, what we call a unit operation, to remove each of those. But every different contaminant is going to have a different reactor system that's going to clean it up. And I point that out because that's one of the downsides of gasification, is every time you put in a unit operation, you put in a few more $1 million into the operation, and after a while it all adds up to a very expensive capital cost for gasification. But it turns out gasification is fairly efficient. People look at, oh, you're burning this material and you've got to put heat into it. Isn't this very inefficient? The answer is no. It actually can be very efficient. Energy efficiency being maximum 100%, we can achieve as high as 95% with certain types of gasifiers. It may be as low as 70 and 90% for simpler types of design. I've already talked a little bit about some of the advantages and disadvantages, but I do need to point out that among the advantages is it tolerates relatively dirty biomass feedstocks. Give us those waste streams wherever they come from. This system will consume them and turn it into a useful intermediate. And that intermediate is very uniform. It's just a few molecules that tend to react well together And so that's an advantage over, say, producing a whole bunch of different sugars or acids or things that often occur in some other processes. And it works. I have to point out that Nazi Germany, when the Allies denied them access to petroleum in Romania, they turned to their chemists and they built gasifiers. They didn't use biomass, they used coal. And they had a substitute. South Africa, during the apartheid era, they were cut off from sources of petroleum. They built gasifiers, used coal, and they still run those today, even past the apartheid era. So it works. The disadvantages is that I've mentioned already, you have to clean up the gas stream. Typically, we'd like to operate these systems at high pressures. Getting solid biomass into a pressurized reactor is not a lot of fun. I'll tell you, we've done it. And it adds to the cost. Both of these disadvantages add to the cost. So typically, they have fairly high capital costs compared to some of the alternatives. Once we have a syngas, we don't want to put that in our engines or even run it into our homes for a substitute for natural gas. It is not of the quality of natural gas. Instead, we want to upgrade it. And there's two basic ways to do that. One is to use a catalyst, metal catalyst, at moderate temperatures and high pressures, and through a number of different technologies can convert that into liquid fuels. On the upper right figure is of a Fischer-Tropsch reactor that is able to turn this gas into a liquid suitable for transportation fuels. But another possibility is shown here. It's called syngas fermentation. What we actually do is run the gas into a fermenter, and there are appropriate microorganisms that are able to take that gas and convert it into liquid products. One most prominently is ethanol, but also can produce lipids that, if you recall, are fairly easy to upgrade. So I'm going to move on to pyrolysis. Pyrolysis is actually very similar to gasification. Some people have trouble distinguishing between the two if you just look at the reactors and think about the high temperatures and process conditions. But more generally, we define it as the thermal decomposition of carbonaceous material in the absence of oxygen. With that definition, it sounds like gasification. But what's different is that there is a multiplicity of products. Depending on how we tune the reactor, we get gas, solids, and liquids. And I'll illustrate here how easy it is to perform pyrolysis. So this is somebody burning the waste material from their gardens in their backyard. So that white smoke is bio oil. And the only difference from what's going on here and what we do in the laboratory is, one, we control the process, and two, we make sure this smoke is captured rather than bother the neighbor. So that white smoke is actually fine aerosols of a liquid that we can capture. When we capture it, we call it bio oil. The many phases of pyrolysis, I mentioned how we control the process will determine the relative proportions of solid, liquid, and gas. The first thing that we can do is called carbonization. And this is a very slow process, and the predominant product is charcoal. So we'll talk a little bit about charcoal later on, but our goal is not to maximize charcoal production, but this is the way they used to do it. They would pile up wood, get a fire going, and then they'd cover it with dirt and basically starve the combustion process, and it would go to a pyrolysis mode, and the result was charcoal. So this in itself is a fascinating process. You'll see this white smoke. Again, they're producing some bio oil here as well, but most of the product is charcoal. Yields of as shown here, up to 33% yield of the biomass. But there's another form of pyrolysis that I'd like to focus on, and we call it fast pyrolysis. Instead of occurring over days, it occurs in less than 5 seconds. It's very high heating rates, and the temperatures are a little bit higher than slow pyrolysis at 500 to 650 degrees centigrade. And this is the product of fast pyrolysis. It is predominantly an oil product, a liquid product. This looks like petroleum. It is not. It has the aroma, if you will, of hickory smoke or barbecue. Some people like it, and some people don't, because this is a very concentrated barbecue smell. Fast pyrolysis, by definition, is a rapid thermal decomposition of organic compounds in the absence of oxygen to produce predominantly liquid product. Contrast this with gasification, which is to produce predominantly gas. So this is a summary of some of the conditions specifically that are required to get liquid predominantly instead of gas. And you can see the yield can be up to 60 to 70% of oil, which is what we want. Now, if you're really interested in what's in this oil, it's quite a long list, and these are family of compounds. These are not specific compounds. But saccharides is sugars, anhydrous sugars is a sugar that's missing a molecule of water in it. So you can see the total saccharides, if you will, can total up to something like 10%. We're working on some technologies to try to double or triple that amount of sugar production. But there are all kinds of other compounds, like this is actually predominantly acetic acid, so a strong vinegar, if you will. Lots of chemicals in there. And it is also an energy-efficient process. We can convert as much as 75 to 8% of the biomass into this oil with an energy efficiency of 70% or more. I apologize for all the emails coming in this morning. It's been a busy morning already. Fast pyrolysis opportunities and challenges. Fast pyrolysis is very appealing to a large number of people, whether they want to grow biomass or produce the biofuels. One of the advantages is the oil is very appropriate for upgrading using petroleum refining technology. And so that means we can produce hydrocarbons using existing infrastructure. And since we've spent billions on infrastructure across the United States to convert petroleum into fuels, it would be nice to use this technology to turn biomass into those same kinds of drop-in fuels. The other very attractive feature of this is we can build these at fairly small scale. Right here is illustrated a quarter ton per day unit. We typically want to scale this up to 50 to 200 tons per day. And you say, boy, it's going to get a lot bigger, but it doesn't scale in volume that as fast. So this notion that we can build fairly small units, distribute them across the landscape, produce an oil that you put in a tanker truck and move to a centralized facility where you would upgrade it, i.e. to a refinery where you would upgrade it to fuels. Now, sounds like lots of important advantages, but there are disadvantages that we're working hard to overcome. One is that there is a lot of water and there's a lot of oxygen in bio-oil as it currently exists. We're looking to drive the water out. We're looking at catalytic processes to get the oxygen out and make it more stable, because right now it is fairly unstable in storage. It tends to thicken up, if you will, which isn't too good if you're trying to pump it around a refinery. The applications of bio-oil, you can use bio-oil as is in stationary power, for example. You just pump it into a burner. We have a faculty member at ISU that has demonstrated that at several different scales. You can produce commodity chemicals. I showed there's a lot of different chemicals. The trick then is how can you get a purified form of it. And there are ways to do that, and we're trying to make some advances in that area. But most of our focus has been in the production of transportation fuels. And I want to point out we can also get lots of sugars and even something we call bioasphalt out of bio-oil. We've got a process where we produce what we call stage fractions. SF1 through SF5. We could increase or decrease that number. And what we're doing is driving the water down to the fifth fraction This is a strong balsamic vinegar, if you will. And these fractions, SF1 and 2, are very dry, and they contain, when we wash this stuff, we wash out the soluble part and discover that it is sugar. And we get a solution that is so highly concentrated sugar that we would actually have to dilute it to use it in a traditional fermentation. We also get the non-soluble part out, and we refer to that as the raffinate. And it is a material that is very, very much like the bitumen that is in asphalt. And we've actually worked with some faculty on campus where we have formulated asphalt substitutes with this material. I can't go away from this talk without mentioning biochar. Any thermochemical process in rapidly heating biomass drives off volatile compounds, gases and vapors and liquids, and leaves behind a solid residue that you look at it and you say, well, isn't that just charcoal? Yes, it's charcoal. And this is a scanning electron microscope of what that charcoal looks like up close. Generally, we've looked at it as a pretty useless byproduct. And my goal has always been to try to minimize the amount of charcoal that's produced. But we're finding out that this charcoal material has some amazing properties that some early researchers discovered when they, in the old days, you used to dump the charcoal out in the back. They find that the plants were growing this charcoal much better than they were in the area surrounding it, and discovered it had some remarkable properties in terms of agriculture or horticulture. This biochar, or some of the inspiration actually came from the Thermochemical soils in the Amazon basin. On the right here, we're illustrating what's called oxysols. You'll notice it is a Mars red color. That means it doesn't have any carbon in it. There's no soil organic matter, virtually. There's a little bit right up at the surface of the soil. On the left here is adjacent soils to these oxysols in the Brazilian basin, Amazon basin. And you'll notice it is full of carbon. Very dark earth, almost look as good as Iowa soils and anywhere in the Midwest. But in fact, this carbon has been measured to be charcoal that deliberately or accidentally was added to the soils. And these soils are much more productive than the soils shown here on the right. And hence, the community of researchers have referred to it as biochar to indicate not only its origins, but its applications. Biochar turns out to have both physical and biological effects. Most prominently, it reduces the density of the soil. It improves the water holding capacity. It holds nutrients in the soil better. And actually reduces the rate of conversion of nitrogen into nitrogen oxides that are emitted into the atmosphere. It also has greenhouse gas impacts. There's a number of them. The ones showing going up would actually tend to increase emissions. But there are a number of things that reduce CO2, or I should say greenhouse gas emissions, for soils that have biochar incorporated in them. And for the sake of time, I won't go into these, but I would encourage anyone that's as fascinated with this topic as I am, is just to Google biochar or terra preta, and we'll discover all kinds of interesting articles on this subject. But why it's of interest to us is it gives the opportunity to improve the sustainability of biofuels agriculture. If you think about it, if we remove large amounts of biomass, we reduce the amount that could be recycled as soil carbon or even the nutrients that are removed, and not used in the fuels, but that are removed from the land. By returning biochar, we're not only returning carbon, but we are returning a variety of nutrients that are found in the biochar, specifically potassium and phosphorus. I think this is just an extra slide here. And some of my inspiration in this area is a fellow by the name of James Lovelock, who has made a lot of observations on the atmosphere, on the operation of the planet ecosystems. He made a statement recently, is there is one way we could save ourselves, and that is through the massive burial of charcoal. It would mean farmers turning all their agricultural waste into non-biodegradable charcoal and bury it in the soil. And there is a lot to be investigated in this area. Iowa State University has committed quite a bit of effort to that, as has the SIN-USA regional project that this is part of. And I want to just end, I guess this is an advertisement for ISU's facilities to support thermochemical research. Much of our work is done in what's called the Biorenewables Laboratory, shown here. And here are a number of the students over the last few years that have conducted research in pyrolysis and gasification and upgrading. And there's also something called the ISU Biocentry Research Farm. It's about 6 miles from the ISU campus that supports pilot-scale facilities. Here's our pyrolyzer, and here is our gasifier unit. Because there's still a lot of questions that have to be answered about thermochemical technologies, but we're discovering that there is a growing interest in this area because of its ability to process a number of types of feedstocks in producing drop-in biofuels. So that brings me to the end of my presentation. I'd be happy to answer any questions.
That's wonderful. Thank you so much, Dr. Brown. We will open it up to questions, and those of you who have questions, please type them into the chat box, and we will get them asked. Talk about there's 3 facilities that are kind of prepped and ready to begin creating biofuels from biomass, and those are Poet at Emmitsburg, DuPont in Nevada, Iowa, and Abengoa at Hugoton, Kansas, all of which are using a enzymatic conversion, it sounds like, to an ethanol. What is the timeline, do you think, of maybe using one of these thermochemical processes to create biofuel on a commercial?
Well, probably by the time they get those operating, they will also be putting in some kind of thermochemical facility. They are going to treat the co-product stream coming from those plants. So the enzymatic process treats only the carbohydrate that is in lignocellulose. So they're doing the cellulose and the hemicellulose, the lignin part of it, the enzymes don't touch. It cannot be fermented. So they end up with a large waste stream, if you will, of lignin. And right now they would propose simply to burn it and generate heat for distillation and drying and that type of thing, which seems a reasonably good application until you think about this is a very valuable material. If it could be turned into fuels, that would add to the bottom line of the plant's profitability. So they are very interested in how could they convert lignin into value-added products. Well, the answer is gasification or pyrolysis. And we've had several companies that are working in this space explore that possibility of how could we use thermochemical technologies to get added value out of the lignin co-product.
So when we built these ethanol plants in Nebraska and Iowa, from 97 to 2006, there was about $1 a gallon capital cost to build a plant. So $100 million gallon plant cost $100 million.
Yes.
And so today the capital cost for cellulosic, they've said, is, I heard somebody say the other day it was 10 times that. And so the question is, what about the capital cost? How does that compare on a thermochemical plant today?
Well, it's the ethanol plant started at $1, and then when there was this frenzy of building them, the prices went up to $2. So it shows how sensitive it is to the market forces acting. Many of the estimates out there are actually based on some analysis done at Iowa State University, and they would estimate these in the range of $4 to $6 per gallon. And Also, you got to remember that's on the basis of a hydrocarbon fuel, which has much more energy in it. So if you correct for the ethanol, which at $1, let's say it's $1.50 or so currently today, and you recognize that you have to multiply that by 1.5 to get it on the basis of a gallon of gasoline equivalent. So now you're up to $2.25 per gallon of capacity. And we're talking about 4 to 6. So we're really talking about a multiplier of 2 to 3 times, not 10 times. Now that's bad enough, but it's certainly not $10. And the capital cost isn't really the final part of this analysis. You have to ask, now when I start that plant operating, what's the cost of the fuel that it produces? And that varies considerably among the different bioenergy options looked at. Pyrolysis actually has an option for producing between $2 and $3 per gallon of gasoline equivalent. And that's not capacity, that's the actual price of a gallon of this product, which sounds pretty good. So you ask, why aren't we building these today? Well, the technology, we still don't have all the engineering data to build these plants and know that they're going to be in the optimal design. Because another important feature is even if we say we can make money by producing fuels in this fashion, you're still going to have to get somebody to loan you the money to build the plant. For a $100 million gallon capacity plant multiplied by this $4 to $6, you're talking $500 million. That's a lot of money, and if somebody's going to invest at that level, they're going to ask, and what's the price of petroleum going to be next year? And nobody really knows. History has suggested that it will go up and down considerably. That may be in the past because now we have China and India and the rest of the world expanding their economies and demanding petroleum. So we may be in a time where it actually would make sense today to start building these plants, but the historical data doesn't support it because of the variability in the past price of petroleum.
Okay, very good. There's a couple more questions, and you might be able to see them there, but one is on the future of catalytic pyrolysis and catalytic upgrading to achieve an economic drop-in fuel. And then the other question, I'll just ask it here, and I've kind of asked this before too, and that is maybe looking on from a biochar perspective, if I put in a ton of biomass, what percent is coming out as biochar, and what can I expect? So that way I could kind of think about how much I'm actually having to put on the landscape and how big of an area I would need to look at to spread that for a plant.
So let me start with the biochar question because that's the easiest one to answer. Pyrolysis typically produces 12 to 15% biochar. The slow pyrolysis can produce upwards of 30% or more, and so that may sound like a better process to produce biochar. We've done an economic analysis that suggests, yes, it may be higher productivity of char, but you don't make money doing it. You need to optimize production of your liquid fuel products and treat biochar as a valuable co-product and accept the fact that you only be generating 12 or 15%. Gasification actually generates a lower level. Depending on the kind of gasifier, it will be in the 5 to 10% range. The other question is about the future of catalytic pyrolysis. And this is something, a wild card in the pyrolysis community. It's something that has emerged just recently, and it's a notion that if you mix the biomass with a solid catalyst, you may be able to have reactions that produce directly what we call the deoxygenated molecules, ones that have very low oxygen with them, so they look like these hydrocarbons that were of interest. Usually it's not a fuel-ready hydrocarbon, but it takes a relatively less amount of upgrading. So this has caused a lot of excitement. In fact, a lot of the emphasis today is on catalytic pyrolysis versus the more conventional pyrolysis. But I I say we tend to get excited about things we know the least about, and this is an area that is so new that we still don't really understand what is happening during this catalytic pyrolysis. And if we can understand that, we may be able to improve it, because right now it's not going to be economical. Typically, and that's my opinion, I need to say, today the yields of the useful compounds are so low that the economics don't work out. We published some in that area looking at that, and we're writing some more papers to evaluate that. What we have to do is get the yields of these more useful compounds up. What happens is a lot of the carbon that is in the feedstock, instead of being converted to these hydrocarbons, gets converted into, guess what, biochar. And as I've already said, biochar today does not have has a much lower economic value than the liquid fuels, and so it's hard to make the numbers work out with it. Ultimately, we may be able to improve on that.
Well, if we have any other questions, bring them up now, but I'd like to thank Dr. Robert Brown for speaking to us today. It was an excellent presentation, and sorry for the technical difficulties we had, but thank you for putting up with that, Dr. Brown. It was worth it, definitely. I learned quite a bit every time I hear your presentations, and I really appreciate you joining us today.
And I see there is a question about the value of co-products. The value of the co-products are generally, we classify them as the biochar. And if you took a hard look at what that value would be, it's only, it's as low as $20 a ton if you're just going to burn it, because you're competing with coal. It's as much as, it's been as much as something like $40 a ton if you were going to sell it in Europe for offsetting carbon credits, because once you bury it, it stays in the ground as a soil organic matter. But if it has additional agronomic value, which we believe it does, that value could go considerably higher than the $40 per ton. Some people have placed it north of $100 a ton. I would say I would rate it more like $100 a ton. But that's still a lot less than the value of gasoline, which can sell, on the order of $600 a ton or higher. So that's one of the issues there. Looks like there was one more question. I don't know if I can scroll down to see it.
Yeah, the last question is, it says research on yield response to biochar.
Okay, so this is an area that there's a lot of excitement about, again, because we don't know very much about it. But there is a lot of compelling early evidence that the yield response can be excellent. And the good news is the poorer the soil, the better it responds. I have received anecdotal evidence personally that on a very poor soil, i.e. one that is an extremely sandy soil in more tropical parts of the world, the response can be such that it could double the yield of a crop. In Iowa, we've done some work and seen yield responses that are like 3 to 4%. Now, that didn't sound very impressive, but if you work out the economics of a 3 to 4% increase for several years, it is a very significant return on investment. Because this 3 to 4% is from a one-time application of the biochar. It stays in the ground and continues to produce a good result. I see one more. What is the effects from ash content in different biomass for pyrolysis? Excellent question. Different biomass starts with different amounts of ash. Different thermochemical processes convert different amounts of the carbon and hence can concentrate the organic matter more or less. And we've seen chars that have as little as 10 or 20% of ash in it, up to 50% ash. And you'd say, well, that's not good news. Why would I want to buy the ash? I want the carbon effect. Well, you've got to ask what the ash is. And if it's potassium and phosphorus, you might think differently about saying, I don't want the ash. And in fact, a good part of that ash is represented. Sometimes it's simply sand, though, a silica, and that doesn't generally add too much value to the biochar.
Great questions, and thank you very much. We're going to go ahead and sign off, and we thank you very much, Dr. RBrown. Next month, we'll have our web seminar on, let me check my calendar, I'm sorry. We'll have the seminar on June the 29th, and our topic is, we're going to stay on this topic of thermochemical conversion, but we're going to talk about torrefaction, and we have a company from Kansas that is going to talk about their torrefaction process. And so Kansas State University and Ed Brokish is going to help us set that up and be our host for that day. So June the 29th, come on back, and also we will be trying to get this edited to get out all our little problems and get this up on the web for in the recording. So thank you much, Dr. Brown.